quick as I usually do. So law of conservation. And so when we start using things that aren't just moles, we really have to consider this. And that the total combined mass of the reactants, so the things going into the equation, must equal the total combined mass of the products. So if we're thinking of a generic reaction as such, the mass of the reactants has to equal the mass of the products. And so this idea is super simple. So these problems are just simple algebra. Key here is going to be writing the chemical equations. So if we have 35 grams of nitrogen gas reacting with hydrogen gas to produce ammonia gas, how many grams were reacted? So first we have to write the chemical equation. So nitrogen, what's special about it when we write its formula? N2, it's a diatomic molecule. So nitrogen gas is N2. I'm just going to write G for gas. We're going to be adding that to hydrogen gas. Is hydrogen diatomic? Yes, it is. So you have to write H2. That's going to go to ammonia, which I don't expect you guys to know this exactly, but ammonia is NH3. Is this balanced? Okay, awesome. Hold on, I'm going to change attendance real quick here. So how should we balance it? 2 in front of what? Okay, and then what else? Okay, awesome. Oh, sorry, I'm doing multiple things at once right now. Okay. All right, so we are putting a 2 in front of ammonia and a 3 in front of hydrogen. Now we're balanced. Now, this was just practicing. For figuring out the mass, if I tell you that 35 grams of nitrogen was reacted with some amount of hydrogen, that has to be equal to the 42.5 grams of product. So X is just as simple as 42.5 minus 35. Oops, if I wrote that though. Which is equal to 7.5 grams of hydrogen gas. So pretty simple, but the concept is very important. So let's try another one. I want you guys to try to write out this chemical equation and get it balanced. And the key, I'm going to give you guys a little hint, decomposed. So think about what goes where on the side of the reaction arrow. Or think about what's being formed and what side that should be on the reaction arrow. So aluminum oxide, does that go on the left or right side of the arrow? The left, it's being decomposed. And so aluminum, which has a +3 charge, is going to mix with, not +2, -2 charge for oxygen. So you need 2 aluminums to 3 oxygens. And so aluminum oxide is decomposed to aluminum, which can just be written as monatomic, but oxygen is diatomic, so we write O2. In order to balance this, we have to put a 2 in front of aluminum oxide. That leaves us needing 4 in front of aluminum and 3 in front of O2. Is this what, I don't know if you guys finished, but if you did, match? Okay. So again, super simple. We are just told that we have 45 grams of aluminum oxide, and it's asking how much of aluminum with 21.1 grams of oxygen. So X grams is now equal to 45 minus 21.1, which is 23.9 grams of aluminum. Any questions on this? Okay. All right, so let's actually dive into what stoichiometry is. So our unit on the mole is really gonna come in handy here because stoichiometry is the use of mole ratios. And this is used to determine how much of a substance you have if you know how much of the other. So for example, for the problem we just did, if we know how much we have of aluminum oxide, we can determine using stoichiometry how much we'll produce of aluminum and oxygen. So this is really important in industry because you can determine how much of the reactants you'll need in mass, or you can determine how much you'll produce. And so we'll do some examples of that. And so such an easy thing to relate this to is cooking. Because let's say you have a plan, your original recipe, you're going to make 4, it serves 4, you have your sibling and your parents, you're going to make breakfast. And all of a sudden, both sets of grandparents show up. What do? You just double the recipe, right? And so in doubling the recipe, you have to just double all the proportions or else it won't turn out right. So if you can relate stoichiometry to cooking, honestly, a lot of chemistry is related to cooking. It's funny. I always have students ask me if the water's boiling yet, and I go, well, would you put noodles in it? So I know I was that TA. So I was saying, so like, for example, we have to boil water to do experiments, and a student asks if this is boiling, I would say, well, would you put your noodles in it? So anywho, yes. Oh, thank you. I need that. Okay. So, oh, did this just double? Okay. Now the same, all right, let's focus back up, guys. I'll tell less stories if we get too squirrely every time I do. This same concept applies to chemical reactions because these coefficients that we use, they let you know the proportions. Oh, why Zoom sometimes doesn't work. The proportions that you need of the species to make another proportion of moles. So we're going to talk about one of the most used processes. It's called the Haber process. So this is really important in farming. And so they make ammonia by adding nitrogen gas with hydrogen gas. And so if overall we look at this, what this process is telling us is that there's actually an imaginary 1 here. So we have to think about that. But we have 1 mole reacting with 3 moles of hydrogen in a 1 to 3 mole ratio. And then we get 2 moles of ammonia out. And so what if a company wants 10 moles? What do you think we do? What's our factor we're going to consider? What factor are we going to have to scale up our recipe if they want 10 moles? What do we multiply it by? 5. Thank you. So if we want 10 moles, what is 10 divided by 2? This is, okay. So let me say it like this again. A recipe gives you 4 servings. You now need 8. What do? Okay. Now our recipe says we get 2 moles of ammonia, but we want 10. What do? Does that make more sense? Okay. That's of the reactants going in. But right now we're focusing on the moles of ammonia. That's our product. So think of the 1 and 3 being the eggs, the milk. Yeah, exactly. And so do we have a question? I don't want to think questions aren't allowed. I don't want to yell over you guys. So, and I don't know if you have a question if you don't ask me. Okay, are we ready to carry on? Okay, so if we scale up by a factor of 5, what we're going to be doing is multiplying 5 by the 1 mole. That gives us 5 moles of N2. We then are multiplying 5 by our 3 moles here. That gives us 15 moles of H2. And then if we multiply 5 by 2, we get our requested 10 moles. Are there any questions about multiplication? Okay. So unfortunately, it's not always a convenient request. Let's just say that instead of 10, someone wants 34.338 moles. Nicely, we have an equation to figure this out. And so it seems like a lot of words, but hopefully once I give a couple examples, it'll start to make sense. So your moles given of a species, for our example, I'm going to highlight because I think it'll make more sense. Moles given of species in our example is going to be this 34.338. Then we have a coefficient of the given compound from the original equation. And so since we're still working with the one above, our coefficient is going to be, I'll use a different color actually. Is going to be 2, because that's our given coefficient. Then the coefficient of our target species. Oh, am I doing this backwards? Hold on, let me make sure I got this right. Nope, I'm good. And then our target species will be, okay, we're asking how many moles we need of N2 and H2. So right now our target species we're working with is N2. And our coefficient of N2 from the equation is 1. I'll write that in here. So it's actually pretty simple. How you set this up then is 34.338 moles of NH3, because that's the moles given. And now we're just finding the ratio of NH3 to N2 to figure out how much N2 we need. So for every 2 moles of NH3, we need 1 mole of N2. So we're just halving our original number. That gives us 17.169 moles of N2. Any question? Yeah. I didn't have the coefficients. I used the coefficients to show that you need half as many N2 parts as ammonia. So where the 2 comes from is this part of the equation. Where the 1 comes from is this part of the equation.
So why is the N2 and 3?
Because we're figuring out how much N2 it takes to make that much. We're figuring out the initial amount of moles of it we need. Okay, any other questions? Okay, let's do hydrogen now. So I'm going to erase some of the, because now this is going to change. And our target now is going to be hydrogen. So we are going to, again, start with our, what we know. We know we have trying to get 3.338 moles of ammonia. So how much hydrogen do we need? Well, we still have 2 moles of NH3. That does not change. But it takes 3 moles of hydrogen. So what we're ultimately doing is multiplying it by 1.5. And then you get 51.507 moles of H2. So this, again, seems wordy, seems kind of like a long equation. But the biggest thing you get out of this is if you start with some mole amount of something, you just use the ratios from the equation to do a molar conversion. So start with ammonia. If you want to go from ammonia to nitrogen, well, it's a 2-to-1 ratio. So you just use those in the equation. Okay. Any questions before we move on? Okay. Let's just do one for sodium and water. How many moles of Na are needed to make 4 moles of H2? So our given is this 4 moles of H2. I'm going to call that my given. My target is moles of Na. So if we start with our given, we have 4 moles of H2. What should I put as my bottom part of my molar ratio here? What are we canceling out? H2. And so how many moles in our equation are there? What's our ratio from the equation? If there's no coefficient in front, you put a what? 1. So there's 1 mole of H2. So I'm getting this 1 from the chemical equation here where the imaginary 1 would be. Then our target is sodium. What is the moles from sodium from the equation? 2. Oh my gosh, stop that. So this comes from this part of the equation. So all we're just doing is a conversion of molar ratios. Yeah.
So can you pull the 1 from the reactant, sorry, the product side, and the 2 from the reactant side?
Because hydrogen's on the product side and sodium's on the reactant side. I mean, I'm sorry, that sounded like jerky, but so pretty much you can do conversions no matter. So the goal of stoichiometry is, I know, let's say I want to make 4 moles of hydrogen. How much sodium do I need? This is how you figure it out. So it's gonna come from both sides. I'm sorry. I feel like I was just a big old snot. But I don't want you, I want you to ask questions. This last thing I want is you to stop doing that. I love questions. So, yeah.
So you would not include the sodium as part of the compound?
No. So it specifically says Na. Yeah. So you treat them all as their own species. Okay. So what do we get? You guys can do this math in your head. There you go. 8 moles of sodium. That's how much you need to make 4 moles of hydrogen gas. All right, we're gonna call this advanced stoichiometry. Pretty much, unfortunately, but it also makes sense. You don't go to a company and order moles of something. You want it in grams, liters, a different unit. So we're just gonna have to do unit conversions, but guess what is always the central unit to compare between? Moles. So, you know, it's so funny. Where's my little mole? So I always laughed. Okay, this is so funny. If you write like an equation, I don't know what, this is like the most memorable thing from my chemistry class. It's so nerdy. And if I tell you that I have 2 grams of hydrogen and I want to know how many grams of water I'll make, you have to first convert to moles. Then you can compare moles to moles, and then you have to get back to grams. What do moles like to do? They like to dig. So you have to first dig, change it to moles, convert between moles, and then go back to grams, okay? You know, or maybe you should make comments. Okay, anyway, that's my cheesy chemistry thing. So this is the process that we're gonna learn. Because you guys, what do you already know? What can you use to go from a mass to moles? Molar mass. Then going from moles to moles is what I just taught you, using the ratios of the equation. Now, what if this was liters of water? What do you use here? 22.4. So you guys already have the tools in your tool belt. We're just going to learn how to make predictions using chemical reactions, okay? So the steps here is that you're identifying the given and the target. You're converting things to moles, then multiply by the mole ratio, and convert back to whatever the target unit is, okay? Let's do some practice. Oh, I forgot to erase this page. Don't look. Oh, no. Okay. Okay. So I'm laughing how red his face is. Okay. So guys, I might just have to re-record 7th hour's lecture. Given this reaction between zinc and hydrochloric acid, it's asking how many grams of zinc are needed if we want to get 20 grams of zinc chloride. So what's our given? What's it? Pretty much think of your given as your goal. 20 grams of zinc chloride. And our target, grams of zinc. We want to know X grams of zinc. So we start by converting our given quantity to moles. So if we have 20 grams of ZnCl2, what's our little fraction going to be here? At least start with units. What's the bottom unit? Awesome. And then what's the top unit? Moles, because we're always converting to moles. So how do we figure out the bottom one? You find the molar mass using the periodic table. So zinc weighs 65.4 grams, and you're multiplying chlorine by 2, because there's 2 of them, 35.5. You're getting the molar mass. I'm going to write this. Molar mass of ZnCl2. So then what's the number in front of mole on top? 1, because it's per 1 mole. Okay. So we get that and get 0.147 moles ZnCl2. The next thing that we're going to do is what we just learned today. We're going to practice doing the molar conversion. So if we have 0.147 moles of ZnCl2, according to the equation above, what is the coefficient of ZnCl2? Just 1, because it's missing. So we have 1 mole ZnCl2. What about for zinc? Zn, what is its coefficient from the equation? 1, it's also 1. So this is a 1-to-1 molar conversion. Pretty much all we're doing now, Zn, is just changing the species. This doesn't always happen though. And then lastly, we have to figure out moles to the relevant unit. What's our relevant unit here? Grams. So we're converting to grams. So if we have 0.147 moles of zinc, what's going to be our ratio to the right? On the top? Wait, no, on the bottom. Sorry. And yes, we talked about it already. 65.4 is the molar mass of zinc. And you guys will get 9.61 grams of zinc. Okay. Any questions on this process? Or do another practice here. Okay, so the next one is talking about sodium chloride and sulfuric acid. How many liters of hydrochloric acid are produced from reacting 29 grams of sodium chloride? So what's given to us? 29 grams. And what does it want to know? Liters of HCl. So first step is converting moles from our given quantity. So we are given 29.0 grams NaCl. So we're going to use molar mass to convert. So sodium weighs 23.0. And we know that chlorine weighs 35.5. This is grams over 1 mole, or under 1 mole, I should say. This is equal to 0.496 mole. NaCl. And so one little note I want to tell you guys, do you see why it's kind of important to start labeling what species you're working with? Because as you start doing molar conversions, you want to make sure that you're keeping track. Because if you're using molar masses, you got to use the molar mass of the right species. So get in the habit of writing those after your main unit. Okay. If we have 0.496 moles NaCl, what's going to be our molar conversion here? Yep, NaCl. That leaves us HCl on the top. So how many moles to how many moles? Kind of. You're simplifying, but I want you to use the actual coefficients. Yeah. So you have 2 moles sodium chloride for every 2 moles of HCl. Sorry, I used another boring one, but this does reduce to a 1-to-1 ratio. So we're just keeping that same 0.496 moles, but now we're talking about HCl. Our last step here is going to be converting to our target unit. So we want to make sure that we get to liters of HCl. So if we have 0.496 moles HCl, how do we set up the conversion here? We want liters though. So what's our fancy number? 22.4. So for every 1 mole of HCl, 22.4 liters HCl, that's going to give us 11.1 liters hydrochloric acid. So how I showed you guys this is very broken down step by step because I want you to kind of master and think through the process. But typically you do this whole conversion all in one line. So how you would set this up, I'm going to use the same exact example, is you'd start with your 29.0 grams NaCl. Your first step is using the molar mass here, which is I think 58.5 grams NaCl for 1 mole NaCl. So this is just step number 2. Then I'm writing step 3. Now we're going from for every 2 moles NaCl, we have 2 moles of HCl. And then I would do my last conversion going from moles to my target unit of liters. So for every 1 mole of HCl, I have 22.4 liters HCl. And it's going to equal the same thing you got above. And so one thing about this, it's going to save you from getting answers wrong because of what happens when you break steps down. You round too early. So this is a very important reason why, but just showing we have grams of NaCl that cancel here, moles of NaCl cancel here, moles of HCl, and we're left with our target unit. Any questions on the one line? I prefer that you use what's on the coefficients. Yeah. You want to do some stoichiometry?
Some what?
I love, you want to hear what I was telling them? Okay, so there's this unit called the mole in chemistry, right?
Yeah, I've heard of them all. Yes.
Yes, okay, so not a mole, Owen,
That is awesome.
right? And so when we have our fancy chemical equation, and I tell you 2 grams of hydrogen gas, we want to know how many liters it makes of water. I always have to convert to moles first before you can do the travel. Well, what do moles like to do? They like to dig.
What's your goal here? Like control the world? This is awesome. This is like the language that boneheads like me, some of you had.
Oh darn, they probably don't get it then because none of them are boneheads. This is
Where'd you
class
find
is
them
too
all?
small.
My dog needs that.
Mrs. Lee must have left them. There's a box of them in the back, like a box.
Really?
Yes. They smell like you would think a grandma's house would smell. So you're more than welcome to them.
I have a really smart border collie. We're teaching him the names of different stuffed animals and how to go get them. He doesn't have a mole, but he has a moose. He has a moose, 3 different bears with different names. A duck, a snake. It's really hilarious. Go get the duck. He goes.
Okay, you can definitely have a mole. We'll talk. Not this one.
This is the coolest stuff though, kids. Yeah, this is gateway stuff. This is like, yeah. Me, with my degree, if like I stop working here, it's Starbucks or bust. That's the only place I can work. So when you guys see me at Barnes & Noble or Starbucks working there, have mercy on me, be polite. How are you, Mr. Schwartz? I'm fine. You see me wandering around the Maplewood Mall, just lightly grabbing by the arm, maybe walk me back to Barnes & Noble so I can pass my career peacefully there. This stuff is actually useful. That's cool. I like it.
Thanks, Schwartz. Oh my gosh. Whew. Anywho. I have one last thing. We almost made it through it. Also, I have that whole monologue recorded. So that's gonna come back. Anyway. So let's say both target amounts are in liters, and it asks if you have 10 liters to produce something, how many liters will it take to get something else? We'll watch that. It's pretty cool. 10 liters of H2O, if we're thinking of just a generic water, and want to know how many liters of oxygen. Well, what's the conversion for liters? 22.4 liters of water per mole. Oops. How many moles of water from the equation? 2. 1 of oxygen. And then now we have to convert from moles to liters again. So we put 1 mole on the bottom, 22.4 liters. And we get 5 liters of O2. What do you notice about this conversion factor and this conversion factor? They're opposites in the sense that they use the same number, but they cancel each other out. So if you're going from liters to liters, you just have to do a molar conversion or molar conversion. 5 liters of O2.